In this section, we're going to look at some of the unique characteristics and properties of water. So right off the bat, what makes water kind of a unique chemical, and not necessarily something that's bizarre, but some of its characteristics are not necessarily consistent with most other chemicals. So we're going to kind of talk about what some of those properties are and the characteristics they create. Right off the bat, the number one thing about water and what makes it unique is what's called hydrogen bonding. Now you might think, okay, hydrogen bonds, bonding together, it's the bond between oxygen and hydrogen. Well, in reality, it's not really the bond between the oxygens and hydrogens that we're talking about. It's really the hydrogens that are on one molecule that are attracted to lone pairs of electrons on other structures. So for example here, if we imagine each oxygen atom has two lone pairs, what ends up happening is the hydrogens on one atom orient themselves or rearrange in such a way that they are attracted to lone pairs on others. So what you tend to see is these oxygen molecules will rearrange, or so will the water molecules, where we start to see them move. Well, if they move, then obviously the electrons are moving, and what ends up happening is things start to rearrange. And these oxygens line up in a certain way. And again, if we're just imagining these oxygens kind of moving around here, what starts to happen is we see this attraction between hydrogens on one and lone pairs on another. And this pattern just continues. So if you can imagine that this just keeps going on and on and on. Okay? And again, some of these electrons obviously are not wanting to move with the oxygen atom. But you can see the point here. Now, what's the significance of that? Well, what happens is then the hydrogen from one is sort of attracted to lone pairs on another. And we see this webbing effect. Well, this webbing effect then allows oxygen to have some properties and characteristics that makes it seem like the actual bonds are fairly strong, when in reality it's really not the actual bonds are stronger, but it's the attraction between other molecules. So really, what's the best thing to call this? Well, it's not hydrogen bonding, it's hydrogen attraction. Now, big thing here, we'll talk about another property or characteristic. Why is ice less dense than water? Bottom line, why is ice float? Makes no sense. Solids are heavier than liquids, should be more dense, and they're not. Why? Well, you can look at the diagrams in the book, but here's a simple word explanation. In ice, the bonds are more structured. They're symmetrical. They're not moving around as much. They're farther apart. They're less dense. Whereas in a liquid, there's less structure. The molecules are moving around more, therefore they're tighter and they're more dense. Now, if we go back to something in an earlier part of the chapter, kinetic molecular theory. Kinetic molecular theory, for solids, molecules are moving around slower. For liquids, they're moving around faster. So if we can imagine what happens here, because we're talking about water molecules and we're talking about ice, what ends up happening is because these molecules don't move around as much, they get in these fixed patterns. And these fixed patterns create this hexagonal structure. And we get this hexagonal structure, and what we'll notice here is that the molecules kind of form this pattern here. And again, you can kind of see what's going on. But because they're not moving around as much, they sort of fit this symmetrical arrangement. And what we end up finding out is there's a lot of empty space, low density. Well, when there's a lot of empty space and low density, then the solid, because it's going to have less density, that solid is going to float. Now, why do they stay in this pattern? Because again, the hydrogen bonding, the hydrogen attraction. Because they're not moving around as much, um, that's what happens. Now, if we take into account, well, what's happening in liquids, that's a little different. Here's what's happening in liquids. Molecules are moving around faster. Okay, so if we can imagine they're moving around and all that stuff and flying, and what ends up happening is because they're moving around more and flying around, they end up sort of packing in tighter. Because they pack in tighter, there's not as much empty space. So if we can imagine that, these molecules they're moving all over the place. And again, back to kinetic molecular theory, in liquids, they're going to move around faster. Therefore, there's the opportunity for them to twist and turn and intermingle more so than in solids. Now, there's still the hydrogen attraction, but the distance between those is a lot less. Because of that, the liquid is more dense than the solid. And that's pretty much it. The last thing we'll talk about, there is, kind of one calculation here that's important. When we get into later chapters and specifically talk about energy and thermodynamics, we'll revisit this. But here's something just good to learn about water. Two things. One is called the molar heat of vaporization, and the other is called the molar heat of fusion. Quite simply, it is the amount of heat or the amount of energy needed to vaporize a mole of liquid or to melt a mole of ice. Now, vaporization and fusion, these could apply to any chemical. Specifically, we're just going to look at water. So how much heat is needed to change water into steam or water vapor, as well as how much heat is needed to melt a mole of ice into liquid water. Well, if you notice here, MHV, molar heat of vaporization, 40.79 kJ per mole. This is what's called kilojoules. It is a unit of energy. So it's 40.79 kilojoules per mole to vaporize water. It's 6 kilojoules per mole to melt water. So you can see here, it's almost it's a little bit more than 6 times more difficult. It requires 6 times more energy to vaporize than melt. Okay? It takes a lot more energy to get water to go from a liquid to a gas compared to solid to a liquid. Now, is every chemical this way, that the heat of vaporization is greater than the heat of fusion? It really truly depends on the chemical. Most, I would say yes, but we can get some substances where that's not the case. So simply here, we can obviously do some simple calculations. If you're given mass, you can go to moles, and then you could obviously find out how much energy. So if you've got, for example, 100 grams of water, how much energy would it take to vaporize it? Or 100 grams of ice, how much would it take to melt? And then also, if we had a certain amount of energy, how much water or ice could we melt, vaporize, whatever the situation is? Okay. So pretty simple calculations. They give some simple examples at the end of the section. Shouldn't be that difficult. Just remember, treat molar heat of vaporization and molar heat of fusion just like molar mass. Right? Instead of the number of grams per 1 mole, We're talking about the number of kilojoules per 1 mole. But it's a pretty simple calculation. Again, we're not worrying about reactions of any sort. So that pretty much covers water and some of its unique properties and characteristics.